I would now like to ask our first participant to make their way to the front. Our first speaker is Aditya Upreti. Aditya is from the Department of Physics and Astronomy. The title of Aditya's talk is Hunting for Magnetic Monopoles with Large Hadron Collider via the Schwinger Effect. Thank you, Aditya.
Good evening. I'm Aditya. And for the next 3 minutes, we'll be talking about what are magnetic monopoles, why they could hold the secrets to our universe, and how we could discover them. We all have seen magnets around us. A magnet consists of a north pole and a south pole. If you break a magnet into 2 or even 1,000,000 pieces, you'll always have another magnet that has a north pole and a south pole. Individual poles, or magnetic monopoles, do not exist. But there's nothing in our known physics that says that they shouldn't exist. On the contrary, if they exist, they would explain why electric charges occurs in small packets. They would bring symmetry to our known theories of physics, and they're also predicted to exist in several theories of the universe. So there's enough motivation to search for them. But where do we start looking for them? The best place to start looking for them is the largest particle collider on the planet, the Large Hadron Collider. On the border of France and Switzerland lies a 27-kilometer long tunnel, 100 meters below the surface. And inside this tunnel, they move these fundamental particles called protons to very, very high speeds and collide them. And this collision creates a lot of energy. If instead of protons, their heavier cousins, the lead ions, are used, at the point of collision, they create the strongest magnetic fields in the known universe. To get a scale of it, the magnetic field of the Earth is 10 to the minus 4 Teslas. The magnetic field produced in these collisions is 10 to the 16 Teslas. That's 20 orders of magnitude greater. And here's where Schwinger comes into picture. Nobel Prize-winning physicist Julian Schwinger stated that if you have an extremely strong electric field, you can produce electric charges, these electrons, from nothing, from vacuum. If instead you have an extremely strong magnetic field, you can produce these magnetic charges or magnetic monopoles from nothing, from vacuum. And this is what we try to do for the very first time. Our detectors are placed right at the point where these collisions happen, where these new particles would be created, where these strong magnetic fields are formed. And as these particles would be created, they would traverse through our detectors and leave traces in them. And this is what we try to measure. We analyze the data from these collisions that happened 2 years ago. And we analyze these collisions and we place these limits. These limits basically define this energy scale to which we have looked at. And although we couldn't find these magnetic monopoles so far, the Large Hadron Collider is colliding these particles as we speak at even higher energies and even more particles. And our detectors are placed once again to search for the missing piece in the jigsaw, the magnetic monopole. Thank you.
Thank you, Aditya.